Michio Kaku uncovers an astounding discovery. The James Webb Space Telescope has detected a mysterious signal emanating from the Andromeda Galaxy for over a century. How we could interpret Andromeda has largely been earthbound, but with the James Webb Space Telescope, our perspectives are fundamentally shifting. This new information has sent shock waves through established scientists. But what does this remarkable discovery tell us, and why is it causing such a commotion among space experts? Join us as we delve into the nuances of this revelation and explore its implications for how we might interpret our neighboring universe. Before diving into the details of the disturbing signal, it's essential to understand some background about the Andromeda Galaxy. The Andromeda Galaxy was one of the first clues that our universe extends beyond the Milky Way, revolutionizing our understanding and highlighting that we may only be a small part of a vast universe. Initially, the Milky Way was thought to be the entire universe. Early astronomers, using limited technology, couldn't distinguish individual stars within it. This changed with Galileo Galilei in the 17th century, who, using a telescope, observed that the Milky Way was composed of numerous stars. This finding began to challenge the idea that the Milky Way was the only galaxy in the universe. The real game-changer came in the 1920s with Edwin Hubble. Using the Hubble telescope, he identified distant objects beyond the Milky Way, recognizing them as independent galaxies, thus expanding our view of the universe. One of these galaxies was Andromeda, also known as M31. Its observation dates back to the 10th century when Persian astronomer al-Sufi recorded it without the aid of telescopic technology. By the 20th century, technological advancements allowed astronomers to investigate further, understanding that Andromeda was a vast cloud with a massive galaxy of stars, like our Milky Way, but situated about 2.5 million light-years away. Since then, the study of Andromeda has advanced significantly, from ground-based telescopes to space observatories like the Hubble, and now, with the James Webb Space Telescope. Each new instrument has brought us closer to understanding the true nature of Andromeda, helping cosmologists unravel the galaxy's structure and relationship with our Milky Way. The connection between the two galaxies is key to understanding the future of our own Milky Way, especially since they are expected to collide in about 4 billion years. Recently, the James Webb Space Telescope has detected a disturbing signal from Andromeda. So, what does this latest signal reveal? The James Webb Telescope, far more powerful than its predecessors, has captured data from Andromeda that challenges previous understanding. The telescope's advanced sensors have detected unusual activity in Andromeda, differing significantly from past observations. This signal suggests that fundamental processes are occurring within the galaxy, potentially linked to its supermassive black hole or other unknown phenomena. One key finding is a shift in our understanding of Andromeda's size. Estimates once suggested that Andromeda was much larger than the Milky Way, but new data suggests the two galaxies are more comparable in size, reshaping our understanding of the structure of our universe. Furthermore, the James Webb Telescope has provided clear images and spectra of Andromeda, revealing new star formations and chemical compositions. These details are crucial for understanding how galaxies evolve and what conditions may lead to the emergence of life. Another significant revelation involves the active galactic core of Andromeda. The data shows that the supermassive black hole at its center is more active than previously believed. This activity influences the surrounding area and may impact the overall structure of the galaxy. The telescope's findings also contribute to solving the mystery of dark matter by studying the gravitational effects on stars in Andromeda. Researchers hope that by examining these effects, they can better understand how dark matter is distributed throughout the universe. These new revelations from the James Webb Space Telescope have sparked numerous investigations. Scientists worldwide are analyzing the data to uncover more of Andromeda's secrets. Each discovery helps piece together the galaxy's history and future, offering a clearer picture of how the universe operates. Andromeda, our closest galactic neighbor, possesses several unique characteristics that captivate astronomers and set it apart from other galaxies. For one, Andromeda's size is impressive. Recent data suggests it spans about 220,000 light-years across, making it one of the largest galaxies in the local group, much larger than the Milky Way. Its vast size contributes to its mass, containing an estimated 1 trillion stars, outnumbering those in our own galaxy. Andromeda's structure is also intriguing, with a typical spiral shape, but a bulging center surrounded by rings of dust and gas that are sites of active star formation. These features indicate a dynamic galaxy, with ongoing processes that shape its appearance and evolution. The center of Andromeda is particularly fascinating because it hosts a double outflow, suggesting it harbors a supermassive black hole. Additionally, Andromeda is surrounded by a halo of cosmic material extending thousands of light years, composed of stars, planetary nebulae, and globular clusters, providing evidence of the galaxy's complex development and history. The globular clusters are especially interesting, with over 460 identified, offering clues about the early stages of the galaxy's formation and the dynamics of star clusters. Another unique aspect of Andromeda is its satellite galaxies. More than 20 smaller galaxies orbit Andromeda, some of which are being stripped of their stars and gas, contributing to Andromeda's growth. This process, known as galactic cannibalism, highlights the aggressive nature of galaxy evolution and offers a real-time example of how galaxies interact and evolve over time. But how is Andromeda evolving, and what does its future hold? The evolution and eventual fate of the Andromeda Galaxy are subjects of significant interest in cosmology. One critical aspect of Andromeda's evolution is its potential transformation from a spiral to a ring galaxy. Observations suggest that changes in its structure could lead to this rare formation, typically occurring after a collision or close encounter with another galaxy. If Andromeda is indeed transitioning into a ring galaxy, it would indicate a history of interactions with other galaxies. Andromeda's future is closely tied to its impending collision with the Milky Way. Estimates predict that in about 4 billion years, Andromeda and the Milky Way will merge. While this event may seem catastrophic, it is a natural part of galactic evolution. Impact won't include direct crashes between stars due to the tremendous distances between them. Anyway, the gravitational forces will reshape both universes during the consolidation. Gas and residue from the two universes will cooperate, driving to new eruptions of star formation. This eruption of divine creation will enlighten the consolidating worlds, creating a novel and staggering enormous event. The impact will eventually result in a single curved system, an interaction normal in the universe's history, but remarkable in human terms, given that our direct contribution to these events is extremely unlikely. The extremely large black holes at the centers of the two worlds are also expected to consolidate. This event could bring about significant emissions of radiation as matter is consumed by the newly formed black hole. Zeroing in on this process gives insight into the life cycles of galaxies and the role of black holes in their evolution. So, what does the eventual fate of Andromeda and its normal consolidation with the Milky Way mean for the destiny of our local group? While the fact that the planetary system makes it impossible to be destroyed, its position and conditions could change significantly. This includes possible shifts in orbit or, alternatively, ejection from the newly formed system. Understanding these processes helps scientists predict the outcomes of similar events elsewhere and provides context for the potential fate of our own planet. The study of Andromeda's future development is about understanding the forces at play and the inevitable evolution of galaxies over billions of years. The expected consolidation between our galaxy and Andromeda raises critical questions about its impact on Earth's environment. It is essential to understand that the immense distances between stars mean that direct star-on-star influences are unlikely. However, the gravitational effects of such a consolidation would be substantial. The consolidation could disturb the stable orbits of stars, potentially sending many of them, including our Sun, into new directions. This change in position could have significant consequences for Earth's climate. If Earth's distance from the Sun changes substantially, it could either warm or cool, depending on the direction of the change. A warmer environment could lead to melting ice caps and rising sea levels, while a cooler environment could trigger a new ice age. Furthermore, the consolidation could lead to increased radiation reaching Earth. As the Milky Way and Andromeda's black holes approach each other, their interactions could accelerate particles to high energies, increasing the amount of radiation entering Earth's atmosphere. This rise in radiation could have detrimental effects on Earth's ecosystems, potentially leading to increased mutation rates in organisms and affecting biodiversity. Changes in Earth's orbit or axis could also disrupt the distribution of climates across the globe. Some species could thrive under these new conditions, while others could face extinction. Moreover, the consolidation might trigger new star formation as gas clouds from the two galaxies collide and compress. If this star formation occurs near the planetary system, the radiation from these new stars could further affect Earth's environment, impacting climate and life. However, it is important to note that these events are projected to happen billions of years in the future. Human existence, by then, may have evolved significantly, or our species might occupy different parts of the world or universe. The discoveries from Andromeda have significant implications for understanding our galaxy and its future. The comparison between Andromeda and the Milky Way helps astronomers better understand the structure and development of spiral galaxies. Observing Andromeda's features, like its spiral arms and the movement around its supermassive black hole, provides a reference point to focus on similar features within the Milky Way. This comparative study refines our models of galaxy structure and evolution. Additionally, the discovery of Andromeda's size and mass has direct implications for how we interpret the Milky Way. Initial assumptions suggested Andromeda was much larger than the Milky Way, but recent data indicates that the two galaxies might be more similar in size than previously thought. This challenges our perspective on the Milky Way's position in the local group of galaxies and its gravitational influence. Although the Milky Way is currently a spiral galaxy, interactions with neighboring galaxies, particularly Andromeda, could alter its structure. Understanding Andromeda's evolution gives clues about the events that lead to such massive changes in galaxy morphology. By focusing on Andromeda's current status and predicting its future direction, astronomers can simulate the effects on the Milky Way, including changes in star formation, the distribution of gas and dust, and the dynamics of both galaxies. The field of astronomy has undergone massive changes thanks to technological advancements. From the earliest telescopes to the sophisticated observatories of today, each step forward has expanded our understanding of space. The journey began with the invention of the telescope in the early 17th century. This simple device, consisting of lenses within a tube, allowed astronomers to observe Jupiter's moons and Venus phases. Over time, the size and power of telescopes grew. The 19th and early 20th centuries saw the development of larger, more powerful telescopes, which allowed astronomers to look deeper into space and discover new celestial bodies, like Neptune. However, these ground-based telescopes had limitations, primarily due to atmospheric interference and light pollution. The launch of the Hubble Space Telescope in 1990 marked a significant leap forward. Positioned above Earth's atmosphere, Hubble provided clearer, deeper views of the universe than ever before. Its observations have led to breakthroughs in our understanding of dark matter, the age of the universe, and the development of space. Following Hubble, other space telescopes, including the Chandra X-ray Observatory, have further advanced our knowledge of the cosmos. The Spitzer Space Telescope has noticed the universe from space. Nevertheless, optical telescopes, radio, infrared, and X-ray observatories have extended our enormous toolbox. These instruments permit stargazers to identify and study peculiarities like the universe's microwave background radiation, star formation regions, and the remnants of cosmic explosion blasts. Dark matter remains one of the universe's greatest secrets, undetectable yet containing a critical piece of the universe's mass. Dark matter doesn't radiate, ingest, or reflect light, making it undetectable by conventional means. Rather, its presence is deduced from gravitational consequences for visible matter, radiation, and the large-scale structure of the universe. In Andromeda, evidence for dark matter comes from the universe's rotational speed. Stars close to the galaxy's edge turn at comparable rates to those near the center, in opposition to what might be generally expected if only visible matter were present. This uniform turn rate suggests a huge amount of concealed mass credited to dark matter, wrapping and impacting the galaxy. Observations of Andromeda also reveal an enormous corona of dark matter extending a long way beyond the visible stars. This corona influences the movement of satellite galaxies and star clusters orbiting Andromeda. By focusing on these orbital movements, stargazers can gauge the mass and distribution of dark matter within the galaxy. Such studies show that Andromeda's dark matter halo is both massive and broad, extending more than 1 million light-years from its center. The distribution of dark matter in Andromeda is not uniform, it is denser near the galaxy's center and becomes less dense outward. This distribution influences the formation and evolution of stars and gas clouds within the galaxy. Dark matter's gravitational pull helps shape the winding arms and impacts the rate and location of new star formation. Moreover, dark matter is believed to play a crucial role in galactic interactions and mergers. The ongoing impact between Andromeda and the Milky Way, for example, is also a result of the immense dark matter halo surrounding the two galaxies. The dynamics of this impact, including the potential state of the merged galaxy, will be significantly influenced by dark matter. The new discoveries from the Andromeda galaxy have significant implications for how we interpret the universe. Andromeda's findings provide crucial information on galaxy structure and evolution. By observing Andromeda's structure, cosmologists gain insights into how galaxies develop over billions of years. This includes the formation of spiral arms, the growth of central bulges, and the role of collisions and mergers in shaping galaxies. Understanding these processes in Andromeda helps astronomers refine models of cosmic evolution across the universe. Andromeda's discoveries also contribute to the refinement of the universe's distance ladder. By measuring distances within Andromeda and comparing them with those from other galaxies, astronomers improve the techniques used to determine astronomical scales. This is essential for assessing the expansion rate of the universe, a key parameter in cosmology known as the Hubble constant. Furthermore, the study of Andromeda's stellar population and chemical composition offers insights into the life cycles of stars and the distribution of elements across the universe. These discoveries help cosmologists understand the processes of nucleosynthesis and chemical enrichment that occurred in the early universe and continue to happen within galaxies. Space exploration, while advancing our knowledge and technology, presents environmental challenges. The launch of rockets, for example, releases pollutants into Earth's atmosphere. Rocket fuels emit chemicals like chlorine and alumina, which can harm the ozone layer and contribute to atmospheric pollution. Debris is another critical issue. Space missions leave behind garbage or space junk, ranging from spent rocket stages to broken satellites. This debris orbits Earth at high speeds, posing collision risks to operational spacecraft and satellites. Efforts to track and remove space debris are ongoing, but the growing number of objects in space makes this an increasingly complex environmental challenge. On planetary surfaces, pollution is a concern. Rockets visiting other planets or moons can carry harmful microorganisms, risking contamination of these environments. This is especially important in the search for life, as Earth life could complicate the detection of native organisms. Space missions must adhere to planetary protection guidelines to minimize this risk, ensuring that rockets are sterilized and missions are carefully planned to avoid environmental contamination. Light pollution is a frequently overlooked consequence of space activities. Satellites and large star clusters, like those used for global internet coverage, reflect sunlight back to Earth, obstructing cosmic observations and altering the overall view. The study of the Andromeda galaxy offers valuable insights into the universe's structure, evolution, and future. By comparing Andromeda to the Milky Way, astronomers gain a better understanding of galactic dynamics. Observing Andromeda's characteristics, such as its spiral arms and active supermassive black hole, provides a reference point for studying similar features within the Milky Way. This comparative approach refines our models of cosmic dynamics and evolution. Furthermore, the discovery of Andromeda's size and mass challenges previous assumptions and reshapes our perspective on the Milky Way's place in the local group of galaxies. Understanding Andromeda's evolution provides clues about the events that lead to massive changes in galaxy morphology. By modeling Andromeda's current state and predicting its future trajectory, astronomers can anticipate the effects on the Milky Way and refine models of cosmic development. However, space exploration also presents environmental challenges, including pollution and contamination, which must be addressed to ensure the responsible exploration and preservation of space.